All right, welcome to part one of lesson four. I'm breaking up this lesson in the different sections. So we're going to be graphing polar equations today. And so since we're graphing polar equations, there's going to be different types of shapes that we're going to go through. So rather than just doing one long video, I've decided to do a video on each shape. And so this is going to be our first one for today. But before we get started, I wanted to just kind of go through a couple things that I think will be helpful. So convert the following rectangular equations into polar equations. So we have x's and y's, which are normal equations that we're accustomed to, but we're going to convert them to polar. So remember we said if we see a y, then we're going to do r and then sine of theta equals 2. And then the goal is to get r by itself. So we'll divide by sine. And when you divide by sine, you could say r equals 2 over sine of theta, right? That would be something you could say, or you could even go r equals 2 cosecant of theta. All right. Next, we have y equals rad 3x. And so I'm going to say r sine of theta again for y. Rad 3 times r cosine of theta. And since we don't have another term, I'm going to actually divide by r cosine of theta. And this guy's going to look like this. The r's are actually going to reduce, and I'm going to say that sine over cosine is tangent of theta equals rad 3. And we said when we get to this point, we essentially are going to just state the angle, that the angle is always going to be pi thirds, or whatever the angle would have been that makes it true. So pi thirds is when tangent is rad 3. All right. And then the last one is x squared plus y squared equals 25. If you remember, we said that when we look for x squared plus y squared, we said that that actually can be substituted for r squared. And so r squared equals 25, get r by itself, so r equals 5. You don't need the plus or minus. So we end up with those answers. Now, before we get started graphing, I want to talk about why did I convert? What's the point of getting to this spot? Okay. So if we were back in, I don't know, algebra 1 in geometry, this is a fact, algebra 1 in geometry, if I ask you to graph y equals 2, you would have made a coordinate plane, you would have put 2 notches, and then you would have put a flat line, horizontal line, and you would have said that is a horizontal line right there at y equals 2. The y value is always 2, there it is, okay? What I'm telling us today is that this polar equation, r equals 2 cosecant of theta, this polar equation graphs a horizontal line. It literally graphs that. Like it's not going to not graph it, not going to graph something different. It's going to graph a horizontal line. It's just this is in polar. So in polar, a horizontal line is written that way, or I suppose you could say that way, 2 over sine of theta. But that's going to be your horizontal line. So kind of weird, but I kind of wanted to point out that this and this are graphing the same exact graph. They're just in different formats, okay? So same thing here, right? If we're in algebra 1, back to algebra 1, and I said, hey, you have to graph y equals rad 3x. You've been like, nope. As a freshman, you would have said, no thanks, or 8th grader or 7th grader, whenever you took it. But how do we graph a horizontal line, right? Y-intercept at 0, 0, and then you're supposed to go up rad 3, which is a little bit more than 1, like let's just say 1.5, up rad 3 over 1. And then you would plot at a point, whoops, sorry. You would plot at a point, and then there's your diagonal line. So we would have ended up with a diagonal line for y equals rad 3x. And I'm saying that this guy right here, okay, graphs the same thing as that, right? So theta equals pi thirds would be a diagonal line still. The last one, this is more of a geometry thing, but sometimes shows up in algebra 1, right? This graphs a circle, okay? So x squared plus y squared equals 25 is a circle with a center at 0, 0. And so if you were to make a coordinate plane, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, say it with me, 1, 2, 3, 4, 5. You put a point out, 5 units, right? And then you would get yourself a circle. So there's your circle. I'm saying that this r equals 5 graphs that picture, but instead of doing it on a Cartesian plane, XY plane, it would do it on the polar plane. So today and for the next few lessons, we're just going to be talking about how do you graph different polar equations. So I'm going to start with familiar things in this video and in the next video, things that are familiar. I'm going to start with lines in this video, and then the next video will be on circles, and then my third video third part will be spirals. That should get wild, and that's where we'll stop for today. And then after this, we'll get into some other kinds of things. All right, so some pretty cool shapes as well, and then you can mess around with it as you find time. So anyway, here we go. Part 1, starting up. So let's talk about polar equations, how to graph them. So the above ones, right, as I was saying, graph things, but now we're going to be here on the polar plane, right? So there's going to be two kinds of lines that are going to be called lines, okay? So these are going to be horizontal lines or vertical lines, okay? So terminology is going to be important. You're going to need to know the names of these different equations, like what they graph. So this would be horizontal and vertical lines. Radial lines, what you're looking for, these are the diagonal lines that I spoke of. So for example, up above, we had r equals 2 cosecant of theta. So you're saying, how would I graph that? Well, first off, you're not going to have to plug points in. This is why memorizing and doing some practice is going to be good. The radius can be identified. The radius can be identified by looking at the coefficient of the cosecant, okay? And so the radius is 2. So at pi halves 2, okay, there will be a point. You say, how would you get pi halves 2? Or excuse me, how do we do it? We do r comma theta, right? So if the point would have been 2 comma pi halves, like how did I know that? Well, I knew that because cosecant of pi halves is still 1. And then 2 times 1 is 2. So there's this point out here. That's the only point I'm going to find. What it's going to do from there is it's going to make a horizontal line, just like that. Okay. The reason we're not going to find any more points is because you would have to plug in, like, say, pi fourths, and the cosecant of pi fourths is rad 2, and then 2 times rad 2 is a number, but I'm sorry, I just don't know 2 times rad 2, but 2 times rad 2 is probably about close to right there. I mean, I might be a little off. You never know. It's not perfectly accurate drawing here, but it's just going to be a horizontal line. If you plug in pi 12th, cosecant of pi 12th is a number, and then you get that multiplied by 2, and it's probably out here somewhere, right? So it would then make a horizontal line, okay? So horizontal lines, all horizontal lines can be written this way. R equals A, I'm going to just use A, and then cosecant of theta, okay? R equals A cosecant of theta. And then A is going to tell you the actual radius, like how far out it should go. Vertical, though, you could probably, vertical, you could probably guess is going to be R equals, and then A secant, or, right, utilizing cosine, a secant of theta. So here, I'll make an example up. Let's do R equals 3 secant of theta, okay? I'm gonna go out 1, 2, 3 and make a point, okay? And then from there, I would make a vertical line to the best of my ability. Probably should get a straight edge, maybe, I don't know. So there would be a vertical line for the same reason, because secant of 0 is still 1. 1 times 3 is 3. Okay, so there we have it. The only question I would ask, if you want to think about it and hit pause, the only question I would ask you is if I make a negative, right? Like what happens? So like R equals, let's say, negative 3 cosecant of theta. Like what do you do there? Let's use different color. R equals negative 3 cosecant of theta. So what does negative radii do in the polar plane, right? So instead of going up 3 at pi over 2, right? When you plug in pi over 2, that's cosecant of pi over 2 is still 1, but then times -3 would be -3 for the radius. And so you wouldn't go out to pi over 2, you would go actually in the reverse direction, right? So 1, 2, 3 down, and you would then make your horizontal line there. So that would be your line, your horizontal line. Okay, so we're going to call those lines, horizontal lines, vertical lines. They're always going to be written in the following way. Okay, a cosecant of theta or a secant of theta. Sometimes you'll see it as like a over sine or a over cosine, but hopefully that shouldn't be a problem for you. Okay, diagonal lines, all right, diagonal lines, to wrap this up, diagonal lines are going to be written theta and then an angle. Okay, so let's talk about what's going on there. So the example up above we had is theta equals pi thirds. Okay, so theta equals pi thirds. What's this saying? This is saying that the angle, no matter what the radius, right? So no matter the radius, the angle is always pi thirds. Well, if the angle always has to be pi thirds, then that means you're always traveling along this line. I mean, any point, no matter the radius, you pick a radius, it's going to be having to be along this line because the angle will always be pi thirds. If the radius is negative, then it would just reflect, right, through the pole. And so then it ends up creating just a diagonal line like that. And so there's your radial line, okay? And consider that to be your diagonal line. So another, I mean, if we make one that's negative, like theta equals negative pi over 4, right? So if the angle always has to be negative pi over 4, that means we're coming over here. Negative pi over 4 comes down to 7 pi over 4. It's just going to be that goes through there, okay? And so should be fine, all right? That's line. So we're going to have regular lines, which will be horizontal and vertical, and then you'll have radial lines, which you just locate the angle, and if the angle always has to be that, it's just a diagonal line there, okay? So that is going to be our first part just on lines. Hopefully that makes sense, and we're feeling good.